Okay, so let's go ahead and pick up where we left off last time. In the last video, we got to this Gaussian blurred image after a pyramid mean shift. All right, so the next thing we want to do is what's called thresholding. So ideally, if everything was perfect and all these grains were just one color and all these boundaries between them were just simply one color, then when I threshold an image like this, what I want to do is turn all the grains into white and then all the boundaries into black. And then my job would be done. This would be a lot easier to count. That's never going to happen because some of these boundaries are lighter than other boundaries. If you look in some of these regions, and of course some of these grains have little spots in them and they're not actually all the same color. So we'll have to do a little bit more, but first we're going to go ahead and put a threshold on this. So there's various methods of thresholding, and you can kind of read about those if you want to play with them. I've got 3 different types here that you could uncomment and comment this one, uncomment that one, and see what the different effects are. But they use just different methods for the thresholding. One uses a mean of neighboring pixels. One uses a Gaussian analysis of the neighboring pixels. The one we're going to use for this is this ODSU, and I'm not going to even get into what that is, but we'll also have this thresh binary, which is going to basically output for us a black-white image. Okay, and then we're just telling it the range of values that we have in our image from 0 to 255 is our grayscale image. And I just put this in here as image to threshold so I could change this easily right up here. So we're going to take a look at the blurred image that we had up here. And this is grayscale. So whatever image you want to put in here is fine, but make sure you put in a grayscaled image. All right. So we'll put the image in and we'll let this thresholding do its job. And then we'll just go ahead and plot. So that's what we've got here. Let me run it, make sure all this is in memory here. So here is our previous pyramid filtered and blurred image. And now here's the image now thresholded. So now this thresholded image is strictly black and white. Okay. So we could call it grayscale in terms of how we map the values that are in it. But now all the values in here are simply 0 for black and 255 for white. So I'll take a look at that for you in a second too. Okay, so we're getting closer to what we need. So let me just go ahead and show you a piece of this thresholded image. I called this thresh. So we're going to go from 90 to 120, so right in here, and from 0 to 20. So yeah, so right in, down this way. Yeah, right in here. So there it is. You can see the spot here is right there. Okay, so I'm just pulling a piece out because I want to show you the data behind this one piece. And it would be too much for the whole image. So if I now, instead of doing image show on this piece of our array of data, now I'm going to just take that same data thresh. I'm going to go ahead and tell it that it's a pandas data frame, so it prints out nicely for me in a table format. And we're going to go ahead and pull off the same pixel points. Okay, so now I'm going to see the data behind the scenes, and you can see indeed that it is a black and white image. Again, the zeros are the black, the 255s are the white. So if you compare these two, right, here's the black spot here. So that's right here. All this little set of zeros. Those are each of my pixels for that little spot. And so you can see that spot is only 5 pixels across by about, 5 pixels high. So that's my little black spot. All right, and then here's the boundary, and here's some white. So that's this black boundary going around it like that. And this white piece. Okay, it's just trying to give you a good representation of what's really behind these images. All right, so that's our black and white. So when you're running through to do the homework, of course, you don't need to be running all of these commands, right? This is just to try and understand what we're doing. Okay. So now we've got our thresholded image. And the next thing we want to do is to apply what's called a watershed algorithm. And the idea with a watershed is that we will take the original image, and let's say that I start it somewhere here with the original image, and well, actually it's going to really start in the dark regions, but let's say we start in here, and then we pretend that we've got water that we're pouring in, and the heights that are in here represent elevation levels, and so the water will start pouring in and filling up this grain, and we'll do that with each of the grains that we identify. We'll let different colored water fill those, and then where they meet is the boundaries. So we're going to have to put this image in a form where that makes sense. I'm going to need to flip things a little so that these boundaries are actually white, and because that represents a high height, and these regions are low. So as I fill up this grain, eventually it will get to this boundary, which is like a mountain that will contain the water as this keeps getting filled up more and more. All right, that's kind of the idea, and the computer will just keep track of that. So to set up for that, what we're going to need to do is play around a little bit with this thresholded image, because there's still some noise in here, and so I want to be able to tell the routine what parts of this diagram that I know are grains. And so, as I get further and further into the center here, I know that is all white and should be white. And so we're going to do some tricks to widen this boundary between the grains to identify spots that we know are grain. And then we're going to do the same thing, but kind of shorten, so we can try and identify what would be a background, and then we'll subtract those images to identify the region, which will ultimately be between the grains, where we don't know exactly where the interface is yet, and that's what the watershed will find for us. All right, I know it's a little confusing, a lot of information, but that's the idea behind it. So we're going to do what's called an opening on our thresholded image, and this morph open, this really just tends to get rid of some noise, and so it does help, especially it helps define the black lines in our image a little bit better. So it's kind of a noise removal. Then we're going to calculate what we call the shore background. So we're going to use something called a dilate, and we're going to apply that to the noise reduced image opening. So the dilate will kind of expand the white regions and start eating up the black regions until we have just a little bit left. We can call that the background. The foreground does the same, because of the opposite. It erodes the white images, allowing the black boundaries to kind of grow in to the grains. And so we call that the shore foreground. So what remains of the white we know is definitely in the foreground. And then if we subtract the two, the background out of the foreground, then what's remaining is unknown. That's what we need to figure out. The boundaries between the grains are hidden in this unknown regions. So that's the idea, and we'll go ahead and take a look at each of these and what they do for our image. Now, in our particular case with grains, we really don't have a background. I included this step here because for other types of analysis where you want to do something like this and find other features, you may indeed have a background. Maybe you've got a two-phase structure and you only want to analyze one of the phases. You could specify the other phase essentially as being the background, and the analysis would ignore it and only count the foreground pieces. Okay. Typical examples, if you look this up on the web, you'll find people using it for like a collection of coins that are sitting on a surface, and they use this to identify the coins from the table surface, and the table in that case would be your background that you want to ignore. Okay, but again, we don't have really a background because the entire image is what we want to try and analyze. Okay, so we ran all of those, and then we're going to go ahead and just plot them all for you. So there's the original image. There's that thresholded image again. This is after we apply the opening filter just to remove a little bit of noise. And it tends to help out with the black lines a little bit. Although in this particular image, it was pretty good from our initial filter anyway, so there's not a lot of change really here. But we applied it anyway because in some cases it really does help. And then we do the background here, and where we dilate or have these regions of white grow and start eating into the boundaries. And in this case, we ran it several times. We ran it 3 iterations. And basically, I tweaked with the number of iterations to where we got rid of pretty much everything. And there's maybe some specks. But I don't really have a background, so I don't want to specify one. So, for example, if we made this, and feel free to play with these numbers and see what happens. But if I made this a 1, then if I go ahead and take a look at my background, it looks like this. Okay, and I really, again, I don't want to specify all of this as background. I don't want it to ignore those regions. I want it to find the interface. So I'll just pick the number of iterations up to essentially where I'm just getting rid of this background altogether. All right, so this is essentially having no background. Then we do the erode, which will grow the regions between the grains. So you can see everything got thickened up. And so these white regions, like we call the shore foreground. So I know that all of this is a grain. That's all a grain. And somewhere between here is the interface that I want to find. Okay. And so if I subtract the background out of this foreground, then I end up with this representation, which in our case is essentially just the reverse of this image, and the inverse of the image, I should say. And now all of the white corresponds to the regions I don't know. And so the program is going to basically look at all of these white regions and allow the water to spread into them to find the interface between the neighboring grains. So that's our unknown region. All right, so I need each of these to run the final watershed. So let's go ahead and do that. So the next thing we're going to do, though, is we're going to go ahead and what's called label our different objects. So we're going to go into that shore foreground where we know that each of the pictures in each of the white areas in this correspond to a different grain. Okay, so we could certainly count the number if we wanted. And what we're going to do with this connected command is it's going to come in and grab one of these white pixels, and then it's going to keep going out and looking at all the neighbors. So every white pixel that touches this, so it'll catch everything in here. It's going to then call count, and it's going to end up putting a label on it. The label is really just a number, so it might call everything in here now. Instead of being called 255, it might get labeled as the 197th grain. And then maybe the next one, this grain will be 198, and this will be 199. So it'll just keep going through and putting integers in for all of the grains in here, and that's called labeling. Okay, so let's go ahead and do that. So we're going to just connect all the white components together. Okay, And as long as it's in the same one, it gets the same number. And we're going to go ahead also and pull out the same exact region as we did here. So this region that was black with this white, okay, that region we're going to pull out here after we ran the connected components. And you can see now that we've got still this black region that actually got a little bigger because of that, the shore foreground picture. But the white around that particular one got labeled as 197. Okay, so these are no longer grayscale values, they're just labels. And then there's a little white piece that's over here that's connected, and so that ended up being called the 212th object. So here's the corresponding picture for this. So all this white that was connected got labeled 197. This little white piece here got labeled 212. Okay, so now we have a way of keeping track of all of the grains through this connected components command. All right, and this is just plotting it and showing it here below. Let's see. Okay, so we have that. We've got all of our grains numbered. Okay, again, what we don't have yet is these black regions. We haven't started to fill these in yet and figure out where the real interface is. So that's what we want to do next. Let's see, when we did this connected components, these were called markers. So this returns two values. Markers is the one we want. That's this image. So you can see that here. I made it a data frame of markers so we could just see it. All right, so I'm going to go ahead and take those markers and I'm going to add 1 to all their values. And the reason I'm adding 1 to all the values right now is because I want to, 0 is ultimately going to be called the background. And so the background we're going to define a little differently. We want to do that from our unknown image, not from the foreground image. So we're just going to call these 1 so that it doesn't get confused with the background. And then I'm going to go and take that image markers and we're going to look at the unknown image. Remember that one is this one here. So all this white is what we're interested in. And I'm going to take all those white values. That's when the unknown is equal to 255. So it goes through all the pixels and it finds all the places where this is true. And then it grabs all those pixel locations from markers that we just had and sets them to 0. So all of the white in this image has now been converted to black. And that is where the low spots are considered, and that's where the water is going to pour in, this water from the watershed. All right, and so then we're going to go ahead and run our watershed using our original image, okay, which is color, the color image, not the grayscale. And we're going to use these markers, which highlight all those unknown regions, as locations for this watershed program to fill and find the interface. And when this is done, this program is done, it will label all of the interface pixels between the grains as -1. And so everywhere the marker now becomes -1, that's what this is going to become now once it runs through here, is the interface. And so we're going to go ahead and find all of those in our original image. And we're going to go ahead and label them. So remember, the original image is color. We're going to go ahead and change the values for all of those to red, right? This is RGB. So no green, no blue, just full 255 red. All right, and then we'll go ahead and plot it, show our image. So here it is. So there's all the red here now is the interface that this watershed found, that it called -1, and then we relabeled as red. So that's how that works. And so that is all of that. Go ahead and run it. I didn't get my markers yet. Okay, there we go. All right, so that's how that works. Yeah, you can see it did a pretty good job. It actually found all of the boundaries right between these various grains. All right, so we're getting there. We're real close now. So let me go ahead and, well, let me do one more thing and then we'll stop, and I'll make another video for the remaining part, which is to analyze it. The next thing we can do, here's that showing that piece again from our image, just how it changed things. So all the zeros are gone. Here's our big region that it's labeled. Okay, 198, this is a label, so this is the markers. And it's now changed, it found the interface, and these are the -1s between them. And here's another grain nearby, which it's labeled as 239. Okay, so what we can do then is use a routine called label to RGB. So it just goes through, grabs all those regions that have integer values, and it puts a color on them. And anything that's 0, it ignores. So it doesn't colorize the boundaries between all of our grains. It ignores those. So anything actually that's 0 or less, it'll ignore. So we're going to go ahead and use the markers. That's this set of data. And it will change all these 198s to the same color, all the 239s to the same color, and it's going to ignore the interfaces, the -1s. Then we're going to also, so that's the marker piece. Then we're also going to use the original image so that we can apply the coloring to it. And this tells it what background label to actually ignore. So that's the -1, the interfaces for us. And the alpha gives the transparency of the coloring. So I made it 20%, actually, I made it 80% transparent so that you could see the original image through the coloring. And then we'll go ahead and we'll call that image 2 now, because this has modified the original image with the color, and we'll go ahead and show that here. And there it is. So if I made this alpha like 1, for example, then we won't see the original image through the picture at all. So it would look something like that, just the colors. So it's kind of nice to let the original image show through a little bit. And there we go. So again, it did a really nice job at identifying all of the grains in this image. Okay, so I'm going to stop there, and we'll come back and analyze now the size of these grains, the diameter of the grains, area of them, and things like that.